Hey, how's it going?
Uh, Good, how are you?
Pretty good.
Good.
All right, so we're gonna start a session. Each of you gonna have 15 minutes for the presentation and 5 minutes for the question and answer. So I will remind you when it's only 5 minutes left, 3 minutes left, and 1 minute left.
Okay.
Let me know when you're ready, and you can share your screen and start. I will start a timer.
I'm ready. Is Dr. Meng ready?
Hey everyone, I'm joining while driving, but I'll make
Uh-oh.
sure my ears are wide open and attentive to the presentation, and I
Yeah,
believe
don't watch.
it is being recorded as well. And David, would you make sure this one, ensure again that this one is recorded?
Yes, right now it's already recording.
Okay, thank you. Good luck. I'm very excited about the presentations today. Thank you.
All right, I will get started. Hello, everyone. My name is Jan McConnell. This presentation summarizes my capstone project, which examines how production attributes relate to audience engagement using IMDb data, demonstrating an applied analytics workflow using SQL for dataset construction, Python for exploratory analysis, and R for statistical validation. I've organized this presentation into three main parts. I'll start by introducing the problem and providing background on how IMDb ratings and vote counts function as observable signals of audience engagement. I will also briefly review related research that examines how ratings-based signals emerge in online platforms and what limitations affect their interpretation. I will also describe my approach, including the data sources, collection, and filtering process, and the pipeline used to construct the integrated data set from IMDb's relational tables. I will then present my analysis and findings, followed by conclusions, implications, and directions for future work, closing with a brief look at my key references before opening the floor for questions. So I wanted
Sorry
to
for
examine.
um, sorry for interrupt. Just wondering
Oh,
if you
I'm
have
not sharing.
share your screen. Yeah.
Yes, I'm so sorry. I don't want to start over, so. Okay. All right. You can see my screen, right? Okay.
Yes.
Okay. So I wanted to examine how observable production characteristics of films relate to audience engagement. And IMDb provides large publicly available data sets that combine film production, metadata, with aggregated audience behavior. And because ratings and vote counts are widely used in analytics, they're often treated as direct indicators of audience preference or film quality. These numbers represent compressed signals of audience behavior and summarize interactions into a small set of metrics, making the relationship between those signals and production characteristics not always clear. So rather than assuming what ratings or vote counts represent, my goal was to analyze how engagement varies across observable production attributes in the data set. And to do that, I constructed a data set from IMDb's relational tables and used exploratory and statistical methods to examine patterns and engagement across genres and other attributes. IMDb data, I'm sure everybody's familiar with what IMDb is. The data that they have reflects real world observational audience behavior rather than controlled experimental evaluation. And these ratings are not collected in a laboratory setting. Instead, they emerge from voluntary participation by users. Ratings represent aggregated numeric scores, while vote counts reflect participation volume. However, these metrics do not capture the reasoning behind a rating or the context in which it was given. Production metadata provides important structure for interpreting these signals, and attributes such as genre and release timing shape expectations, exposure, and ultimately audience engagement. And because this information is distributed across multiple relational tables, schema design and integration decisions directly influence what relationships can be examined in the data set. And this framing explains why interpretation and data structure are central to the project, not just modeling. These engagement signals are also shaped by selection bias and social influence, meaning that observed scores reflect collective audience dynamics rather than just purely independent evaluations. So the literature search for this project overwhelmed me immediately. It initially returned over 4,000 articles related to recommender systems and review analysis. And I want to thank the school for having a great library that includes abstracts for all the papers, because if it wasn't for the abstracts, I would still be reading. So after screening for relevance to audience engagement and rating interpretation, that set, I was able to narrow down to a small group of key studies. And across that literature, 3 ideas consistently appeared. So first, ratings function as a composite engagement signals. A single rating score reflects many underlying factors, including audience expectations, context, characteristics of the film. And second, interpretation often requires additional information beyond the numeric score. And research showed that combining ratings with other signals, such as textual reviews or production attributes, helps explain why audiences respond differently to similar titles. And third, engagement metrics are shaped by participation behavior and bias. Not every viewer rates a film, and those who do may not represent the full audience. So taken together, the literature suggests that ratings should be treated as structured but imperfect signals of audience engagement, which motivates the analytical approach that I used in this project. So I treated ratings and vote counts as observable engagement signals that emerged from a relational production context. The first step was constructing an analytical data set from IMDb's normalized tables using SQL that required careful joins across titles, ratings, crew, genre tables, along with filtering and structured feature construction. Production attributes like genre and release year are treated as contextual dimensions. They are not assumed to cause engagement, but they do allow structured comparison. Engagement volume was modeled using natural log transformed vote counts to stabilize the variance by reducing skewness and to manage outliers. And genre was encoded as categorical indicator variables using dummy encoding with drama as the reference category, so differences could be interpreted directly. So overall, the analysis emphasizes interpretation rather than prediction. And the goal was to understand what these engagement metrics represent, and just as importantly, what they do not represent. So the analytical design began with a set of requirements for constructing a usable data set from IMDb's relational structure. And I needed to integrate multiple tables while preserving the relationships between titles, ratings, and production roles, and to ensure that the data set supported transparent and reproducible analysis. The implementation then followed a very simple pipeline, constructing the data set through SQL joins and filtering, engineering features from the production metadata, and performing exploratory analysis to examine engagement patterns across production attributes. So for my analysis, I used just a small stack of common tools, Python for exploratory analysis and visualization workflows, specifically Pandas, NumPy, and the Matplot library, which is probably my favorite. R for formal statistical validation, SQL for data extraction and integration, SQLite for relational database management, and VS Code for development and version control. The data for my project comes from IMDb's publicly available non-commercial data sets. These are secondary aggregated data sets. No human subjects were involved. The raw TSV files were downloaded and stored locally in a SQLite relational database to preserve the normalized structure of the source tables. Structured SQL joins were used to integrate title basics, ratings, and genre metadata while maintaining relational integrity. Excuse me. The dataset was filtered to include only feature films with complete rating data and sufficient vote counts to reduce instability from sparse observations. And genre categories were retained only when they had enough observations to support meaningful comparison. Finally, it's important to note that the dataset does not include voter level geographic or demographic information. And analysis is conducted at the title level using aggregated engagement signals. It would have been interesting to have that geographical data, though. Maybe another future work topic. So this slide summarizes my workflow, beginning with data acquisition using IMDb's datasets. Those files were then integrated into a SQLite relational database, which allows the normalized tables to be joined and structured for analysis. And then next is feature engineering, where interpretable variables are created from the production metadata. This includes genre indicator variables and natural log transformed vote counts. And after that, exploratory analysis and regression modeling was used to examine patterns and evaluate differences in participation volume. And finally, the results were interpreted in the context of aggregated engagement signals. So to examine the genre effects, I estimated 2 regression specifications. One model includes a control for the number of genres assigned to each title, while the other excludes that variable. As shown here, including the genre count variable produced only a modest improvement in model fit, and the genre count control accounts for how many genres are assigned to a film in order to control for multi-genre labeling to isolate the effect of each genre. So IMDb typically will only allow 3 genres per film. They're not listed in order of preference or primary category. They're just listed alphabetically. So that was kind of an unfortunate thing that I discovered, because it would have been interesting to look at just the primary genre. It was important to me that the estimated relationships remained stable across both specifications, indicating that the main structural patterns are not sensitive to whether this additional control is included. So this figure shows the estimated genre effects on natural log transformed vote counts. Each point represents the regression coefficient for a genre related to relative to drama as the reference category. The blue points are from the model that indicates a control for the number of genres assigned to each title, while the orange points are from the model without that control. Across both specifications, the direction of the coefficients remains consistent, which indicates that the observed engagement patterns are not simply driven by multi-genre labeling. Including the genre count control slightly reduced the coefficient magnitudes, but the overall structure remains the same, which just reinforces that genre identity really is the primary factor organizing engagement differences. So points to the right of the 0 indicate higher engagement relative to drama, while points to the left indicate lower engagement. This figure shows the mean log transformed vote count by release decade. Engagement generally increases across historical periods, reflecting growth in platform participation and exposure over time rather than inherent quality differences between eras. So participation peaks for films released in the 1990s and the early 2000s, and the slight decline for the most recent decade likely reflects a recency effect, since the newer titles have had less time to accumulate votes. Overall, this pattern highlights that engagement metrics are not time neutral and are shaped by both platform adoption and time exposure. Over time, that'll go up, I'm sure. This figure shows engagement levels across bins of credited principals. Reading the bars from left to right, we can see a clear monotonic increase in engagement as the number of credited principals rises. At first glance, the pattern might suggest that adding more principals drives engagement. However, the most likely explanation is production scale, because larger productions tend to involve more credited contributors and typically receive greater visibility and distribution, also marketing. As a result, the pattern likely reflects differences in production scale rather than a direct causal effect of the number of principals. Okay, so several key findings emerged from the analysis, and genre identity shows stable associations with engagement volume. So the direction of the genre effects remains consistent across model specifications, which suggests that these patterns are not driven by multi-genre labeling. Engagement also varies with production and historical content. Titles from different release periods and those with larger credited production teams show systematic differences in participation. And rating level and participation volume behave as related but distinct signals. Highly rated titles do not necessarily receive the largest number of votes. The results were robust across implementations with consistent estimates between Python and R. And taken together, these findings suggest that IMDb engagement reflects participation patterns shaped by genre, production scale, historical content instead of just a simple measure of perceived quality. So the linear trend line provides a simple summary and shows a slight negative relationship, which was a little bit surprising for me, indicating that higher ratings do not consistently correspond to higher participation. The quadratic trend adds more detail, showing that engagement increases into the mid-range of ratings, and then it declines at higher rating levels. This suggests that participation peaks among broadly appealing titles rather than the highest rated ones. So for me, the key takeaway is this: higher ratings do not necessarily correspond to greater voting participation. Rating reflects evaluation, while vote count reflects engagement. So while they're related, they are not the same signal. To summarize my key findings, first, engagement on IMDb varies systematically across genres. Genres such as action, adventure, sci-fi, thriller, and biography tend to receive higher participation relative to drama. And second, production scale is strongly associated with engagement. So titles with larger credited casts and crews accumulate substantially more votes. Third, historical context influences engagement metrics. And this means that vote counts increase across decades as the platform grows, indicating that participation levels are not time neutral. And finally, ratings and engagement represent different signals. And while rating reflects evaluative intensity, while vote count captures participation volume. So overall, the main idea for this is that IMDb engagement metrics reflect a combination of genre identity, production scale, and historical participation patterns rather than just a single measure of perceived quality. So these results suggest several directions for future work. One extension would be to incorporate temporal controls such as release year or decade indicators directly into the regression models to separate genre effects from long-term platform growth. And another direction would be more detailed analysis of production roles, separating actors, directors, and writers to examine how specific creative contributions relate to engagement. And it would also be useful to evaluate whether genre popularity shifts across historical periods by introducing genre time interaction events. From a modeling perspective, alternative approaches like count-based models or quantile regression could help examine engagement patterns across different vote levels. And finally, combining ratings with additional signals such as review text or external performance indicators could provide a richer picture of audience engagement. I did want to include the text reviews, but IMDb only has a data set available to the public that contains 50,000. So, which definitely would not have been enough for my project. Okay, so these results also have several implications for data science practice, and engagement metrics often require contextual interpretation, and platform participation patterns, historical growth, and metadata structure can all influence the signals that we observe. And integrating normalized relational data with engagement measures allows analysts to move beyond isolated rating statistics and examine structural patterns. The analysis also highlights that participation volume and average ratings represent different dimensions of audience behavior. And finally, reproducibility is critical. Replicating the regression models across Python and R helped me confirm that the observed patterns reflect the data rather than a software-specific implementation. And overall, large observational data sets can reveal meaningful structural patterns, but careful interpretation is essential to distinguish engagement dynamics from perceived quality. So just because a bunch of people like a movie doesn't mean that it's going to, guarantee good ratings. And here are some of my key references. And a note on the fifth reference here. I don't know if anybody's familiar with what PACO is. So it's a Bayesian machine learning technique designed to explain user item recommendations by analyzing numerical and textual reviews. This paper was really interesting. And I will leave you with my final thoughts. IMDb ratings and vote counts provide useful signals of audience engagement, but interpreting those signals requires context from participation patterns and production metadata. And one result that may be surprising is that engagement really does not peak at the highest ratings. It peaks in the middle, which suggests that participation reflects exposure and breadth rather than perceived quality alone. I am ready for questions.
I probably have a non-technical question, Jan, but for this, how can this be monetized for films and platforms that are providing these films?
I don't understand what you mean by monetized. How can voting be monetized?
How is this going to impact? I'm trying to follow the money behind this.
Oh.
Is there a way to monetize this for for this platform, or does this mean that they're going to be able to put this on streaming services, or will this be something that can be used to sell the films? I'm just wondering how that works.
I don't think my project can enforce or influence monetization. IMDb does have different subscription levels.
Okay. So there is there could be. I'm just thinking about this for how to move something like this further. Okay, I'll stop asking my.
It's a good question though, because IMDb does make money somehow, otherwise they wouldn't be in business, right? There is no company in business that's not making money that is still in business, unless you're a nonprofit, but you still have some kind of, money coming in, right?
Oh yeah, I mean, nonprofits bring in millions and millions of dollars. It's just
Yeah.
that their model is different. So I want to
Yeah.
defer to other people who may have a technical question for you. And you and I need to talk next week. Okay?
Oh, okay. Okay.
Okay, thanks. Great.
So another thing on that, IMDb does have a paid level subscription where I could have gotten access to all of their text data, but I'm poor, so I went with what was free and what was available. And also, so I do have a pre-recorded demonstration of some of my process on YouTube. You can either go to this link or you can scan the QR code. Thank you, Dr. Meng, for that idea. That's pretty cool. It's already got some views. Any other questions? I've taken 25 minutes. Okay. Thank you very much. Thank you.
Right.
I think Jared's next. Ooh.
Can you see my screen?
I like your
Awesome.
graphic. That's pretty cool.
Thanks. All right. Hello, everyone. My name is Jared Graham. I am presenting as part of my data science capstone. This project's purpose is to examine how process mining compares with traditional process improvement frameworks like Lean, Six Sigma, and theory of constraints, typically used in the production and manufacturing industries. Today, I'll walk through the problem this study addresses, why it matters, the background concepts, related work, and my research approach. Then I'll show how I collected and analyzed the data, what I found from the process mining analysis, and finally, the conclusions, limitations, future work, key references, and questions. The main idea I want you to keep in mind is that this project compares what process mining reveals from real execution data against what traditional improvement frameworks assume about processes. The problem this study addresses is that many organizations still diagnose process issues through manual observation, expert interpretation, and framework-based assumptions. That can work, but it becomes harder as processes become more complex and dynamic. At the same time, organizations now collect much more execution data than in the past. So the question becomes, if I can reconstruct how a process actually ran from event logs, how does that compare to the assumptions built into Lean Six Sigma and theory of constraint? So a simpler way to put it is on the screen. How do process mining insights align with or challenge these frameworks? My motivation is that organizations now collect a large amount of operational data, but that data is often underused. Instead of using that data to understand how work actually flows, many companies still rely on reactive investigation after an incident. So this study is motivated by a practical question. Can data-driven analysis improve diagnosis before improvement frameworks are even applied? Process mining is basically process discovery from system logs. It uses event-level data to reconstruct how a process actually executed. At a minimum, it needs three things to use this technique: a case ID, which identifies one process instance, an activity, which tells us what step occurred, and a timestamp, which says when it happened. This matters because process mining does not start from what one thinks the process is. It starts from the recorded evidence of what the process actually did. These are the three frameworks I compare against. Lean reduces waste, Six Sigma reduces variation and defects, and theory of constraint focuses on bottlenecks. They are all useful, but they became widely established in industry before detailed event level operational data was commonly stored and analyzed at scale. As a result, they were developed in contexts that relied more heavily on observation, expert judgment, and targeted measurement than on full process reconstruction from event log data. Process mining starts differently. It does not assume the process is already understood. It uses event log data to reconstruct how the process actually behaved. The literature shows two things clearly. First, process mining research has already shown that event log analysis can detect delays, rework, bottlenecks, and variability. Second, framework literature shows how Lean, Six Sigma, and theory of constraint guide improvement in practice. The gap is that very few studies directly compare what process mining reveals against the assumptions those frameworks make. That is the space this study is trying to address. My approach combines literature synthesis with an empirical process mining analysis of an event log. So this is not only a literature comparison, and it is not only a technical mining exercise. It is both. The goal is to identify where process mining and the frameworks align, where they differ, and where they might work well together. For data collection, I used two main sources. First, I reviewed literature related to process mining and traditional improvement frameworks. Second, I used an event log dataset for empirical analysis. This dataset is a manufacturing event log representing the execution history of a multi-step discrete production process. Each event records a case identifier with an activity label and a timestamp, allowing reconstruction of individual cases moved through transport, handling, machining, heat treatment, punching, and review-related process steps. The analysis was descriptive and exploratory. Looks like it didn't. There. Presentation is being weird. Sorry, technical difficulties. Let me fix this. Slide. No. Sure. Apologies for that. Okay. This slide shows the actual computational workflow I used. I started with an event log containing case IDs, activity labels, and timestamps. Using Python and Pandas, I validated the required fields and organized the events by case and time. I then computed activity frequency, cycle times, time gaps between consecutive events, repeated activities within cases, and execution variance. Finally, I generated outputs and visualizations with Matplotlib, which became the basis for the findings in the framework comparison. The event log contains 9,471 recorded events, grouped into 301 cases and 21 distinct activities spanning June 2021 through February 2026. A case is one full process instance identified by a shared case identifier, or ID. There were no missing activity labels or timestamps in the processed output. This establishes that the log had the required structure for process mining is complete enough for the analysis. Let's see here. Showing activity frequency. I don't know what's going on with my PowerPoint. Okay, so that's next one. This is annoying. I don't know why it keeps doing this. Very odd. Let me
Gotta love
let me
technology.
let me do this to them. Yeah, it's you gotta love it, gotta hate it.
Yep.
Okay, I just pulled up the PowerPoint, put on another slide instead of using the. Sorry about that. All right, this bar chart shows total event count by activity. The x-axis lists activity labels. The y-axis shows how many times each activity appeared in the full event log. So this is a raw count
Sharing.
across all events.
Not sharing.
It shows. I'm not sharing.
No, sir.
I swear I'm better with technology. It always happens. All right. Can you see now? Take that as a yes.
Yes. Yes. Yes.
Awesome. Thank you. Technical difficulties. All right. This bar chart shows total event count by activity. The x-axis lists activity labels. The y-axis shows how many times each activity appeared in the full event log. So this is a raw count across all events. It shows that execution is highly uneven. A small number of activities account for a large share of all recorded events, while many others appear much less often. That matters because it suggests the workflow is not balanced evenly across its steps. In the literature, this kind of concentration often points to structurally important areas of the process. From a framework perspective, Lean may view this as a flow issue. Theory of constraint may view it as a clue about constraint-related behavior. This histogram shows case cycle time distribution. The x-axis is the elapsed time from the first event in a case to the last event in that same case, or cycle time in hours. The y-axis is the number of cases in each time range. So this chart is summarizing full case durations, not individual events. Most cases finish relatively quickly. Some take much longer. That means the process does not run at one consistent pace. This matters because it shows real variation in execution time, and the process mining literature suggests that this variation is often tied to workflow structure and case path differences, not just final output measures as typically measured by Six Sigma. This chart shows time gaps between consecutive events for selected activities. The x-axis lists activities. The y-axis shows the gap in hours from the previous event within the same case. These gaps are used as waiting time proxies, meaning they estimate delay or inactivity between recorded steps based on timestamp differences. The chart shows median, mean, and 90th percentile values for each selected activity. Most median and mean values are small, which means transitions are often quick. But some activities, especially unload, have much higher 90th percentile values. That means delays are not constant. They occur occasionally in larger spikes. This matters because process mining can reveal those episodic delays even when they are not obvious through normal observation. This chart shows time gaps between one recorded event and the next inside the same case. The x-axis lists selected activities. The y-axis shows the gap in hours from the previous event. These time gaps are used as waiting time proxies, which just means an estimate of how long the process waited between recorded steps. We went over.
You have 3 minutes left.
Oh. That's supposed to I screwed up those notes. All right, moving on. Conclusions. I'll have to fix that. My main conclusion is not just that process mining works well with existing frameworks. It is that process mining changes the standard point, the starting point of process improvement. Traditional frameworks like Lean, Six Sigma, and Theory of Constraint generally assume that important process issues can be found through observation, expert judgment, and limited measurement. Those approaches are still useful, but my findings, together with the literature, suggest that some important issues are not easy to see that way. The event log analysis showed repeated activities, multiple execution variants, uneven activity concentration, and occasional delay spikes. The literature on process mining also supports the idea that waste, variability, and constraints are often embedded in the actual structure of the workflow execution, not just in obvious visible events. That means the problem is not always just one bad step, one delay, or one bottleneck that needs to be patched. Sometimes the issue is the process structure itself, the way cases repeatedly move through the system. So the deeper conclusion is that process mining can expose hidden process behavior first, and then Lean Six Sigma and Theory of Constraint can be applied more precisely afterward. In that sense, process mining is strongest for problem discovery, while the traditional frameworks are strongest for problem solving. That is why I concluded that process mining should not be viewed only as a helpful add-on. It can serve as a diagnostic front end that allows the frameworks to be used more deeply and more effectively. This study has several important limitations. It used a single data set. The analysis was descriptive rather than causal, and it did not experimentally test the frameworks themselves. So this study is best understood as a comparative and exploratory foundation. Future work should expand the number of data sets, compare the frameworks more directly in controlled settings, and potentially add predictive modeling to move from process discovery toward proactive process improvement. Thank you, and I'm happy to take questions.
Very cool. I just have one question. Are you going to be able to use that at work?
Yeah, I could.
Cool. Very cool.
Garrett, thanks for your presentation. What was the most challenge, and also what is your most satisfied achievement in this project?
I would say the most challenging thing was finding a public manufacturing data set that I could use for process mining, um, and and perform empirical analysis on. A lot of this data is held within businesses and companies as proprietary, so that took a while for me to for me to find some. Um, the thing that I got the most out of it. A lot of this stuff I assumed based on my previous experience, work experience, um, was what I thought would happen or what I would find after going through this process. Um, but like I mentioned, it learning more about how one could apply process mining to the existing frameworks that organizations typically use to to improve processes and resolve constraints, and putting together a presentation uh, that could act as a guide for if I wanted to simplify this, I could present it to leadership in my company or other companies so that they could understand more about why process mining is important, why utilizing data science and computer science and technology is important and competitively advantageous.
Good job.
Thank you.
Thank you, and sorry for the technical difficulties.
No worry.
No
Great
worries. Thank you.
presentation. All right, Kayla, you are the next presenter. When you're ready, you can share your screen and start.
Hello everyone, good evening. Myself Akila, and today I'm going to explain about my capstone project. So my topic is like email spam detection technique, which is using by machine learning. So the main the problem statement of my project is so um, so the emails has been everyone will use the emails, right? So either it is a personal or for education purpose or else for work purpose, everyone will use the emails. So it is eco-friendly and also it is quickly available to use. So my main person to select this topic and to implement this project is like nowadays we are getting a huge uh, mails spam mails rather than getting the original mails. So the email are getting full of like the inbox is filling up with lot of stuff like which is spam rather than having the original mails. My main motive is to remove the spam mails, so I want to keep only the original mails in the mail, so that is whatever the junk and the whatever the useless the mails were there, I want to remove from that. So many of us face this issue. uh, Everyone will face this issue while using the emails and everything. So I have researched for my previous papers and all those things. So they were so implementing by the various like filter techniques, so they to remove this spammer. So they were implemented the using the lot of techniques. And So my problem statement and my solution is like I've created like I've used my project by using like Python technology. I have taken I have implemented this project to remove the unwanted messages and unwanted the spam emails from the sorry unwanted spam emails and to block the spam mails, which is easy to Python. Why I choose the Python to implement this code means it is very easy to understand. Python is very friendly and it is easy to implement also, and where it is having the where we'll get a quick uh, results as well while implementing this. So I choose this, and this is the solution for my problem. And coming to background, so in my background, so there are different types of about this project, the data sets we use. So I have used the data set which is this from the Kaggle. I collected the different kind of data sets, but it is very hard to find the data set for me to implement this. But I have analyzed this issue and I sorted out. And my motivation of this project is like like as I said in firstly, so many of us having the personal and academic life, so emails, so everyone used to face this problem having a lot of spam, and this make me motivation to implement this project. And this project is like having a model which is existing method which they use the filter methods. So in my during research, this project is like I am very interested to address this technology in this real world problems where we are facing in our daily lives. So we are getting a lot of unwanted spam mails. So where I define and where I resolve this problem. And coming to related work, so I have researched a lot of papers and I also Googled some regarding this spam detection, email spam detection, where I got to know that it having a lot in around a month. There are using like 10 millions active emails were there around the month, and in that 10 millions, there were only the 57% are only the junk. So it is more higher than the having the ham mails that rather than having more spam mails nowadays. And so to detect this, so to detect this spam emails, so where we need to stop this. And I was so in this having the lot of having fake and unwanted stuff in the mails. For example, many of us got like a short for example, if we got any mail regarding our work or else our studies or something, we having this opportunity, click this and they'll keep unwanted links and unwanted stuff. We might think that it is very useful email, so we will click that and there will be nothing will be there. So that makes us like um first thing time consuming, where our time will be wasted by using those mails. We'll think that it is useful, but the spammer, where they'll create as an it is a real mail. So by having the text format or else the picture format, everything, we might think that. So that is the main issue. And my approach to this project is like applying algorithms to detect the unwanted and we can where we can not to allow the spam emails. So where reputations and everything, so we should not accept the uh, mails which we are getting from the spammers or spammers from to the users. So and this spam emails like it is easy to detect. It is like protecting the customers from the having the information they in our in our mails where there will be a lot of information. So they will they want to take our information, and they want to take our important information where which is very harmful, and which is very affect to our work and everything. So email categorized as in two parts. One is spam and the ham. So I took data sets which I took. So one is ham and the spam. Spam is like unwanted data set, and ham is the useful data set which I used to implement my project. And the data collection. Um, so uh, I have took the data collection. So one is the spam and ham, and in the data analysis where I use the text format and the image format to implement this project. And also I use the techniques that mainly the hybrid bagging techniques and also the SVM techniques to implement, which from the researching papers I got uh, in that. By using those techniques, they got like very uh, results are very high compared to different techniques which were used in the previous researching papers. And I find that, so one thing we should not respond for the spam emails, which will help for us. We should not react, or else we should not respond for that. And also we need to keep it hidden. We need to keep our emails hidden. And also we need to modify the addressing which we are using. And the spam detection method which is comes from the third party only. So the third party, once it enters, it will be getting a lot of trouble to use this. And whereas I use the data set of 5728 emails. So here the 76% are like original mails, like 4360 ham, and whereas like 23% are like spam mails. So I took this data set and I implemented. And in this, this is the modal analysis. So this is the range of the spam, and this is the range of the ham. So in the this is the model accuracy where I got like 98%, 98% of accuracy of having the test accuracy and the CV accuracy of the spam and the ham. And this is the model performance of spam detection. So where I used the four models to implement this, where I got the result as in a 98% of accuracy. First model is like Navi base, and second model is logistic regression, which is very strong and having the better results. And random forest, and having the highest CV accuracy around like 98.5 percentage. And linear SVM, whereas it is having 98 accuracy, which is the best model ever. And this is about the test CV scores. And this key takeaways of my project. And whereas linear SVM is recommended for this model, where I got the 98 99% and uh, accuracy of the detectioning the spam. So this is the mm, top spam keywords of the linear SVM where I use. So, and coming to the conclusion, where it is very email is like very easy to use, and it is very freely to use, very communicate, it is medium of the communication. And when it comes to be like having to detection, we are using the software technology to separate the word communication, like having the tokenization and spamming, and uh, removing the spam word text format and everything, the word to word, which is the useless words, we are removed that. And my future work is like to utilizing the existing and my developing project by using the Python. So my future work is to having like in upcoming days there are the technology is going to increase, and there will be having a lot of AI technology is going to um, implement in further. So AI is also the spammers can take as a like the spammers can take as a tool, like by using the AI they can make a fraud techniques, like having the all the emails and everything. We need to rectify that, and I converted like a raw SMS and text into the punctuations and everything, the stopping the word and everything I did by using the machine learning and the Python. I concluding this project, and this is about my spam detection by using the machine learning. Is there any questions?
So why I have a question. Why did you decide to choose the model for your last application? Is there any other model that you would like to consider in your futures?
uh, the model, uh, so the machine learning model is very useful, so in future as well. So by using that we can develop and we can rectify the problem where we are getting the spam emails and everything. So by using this model we can detect the everything, having a proper data sets and everything.
All right. There's anyone else? I have other questions for Akela. All right, great. So it does conclude our session. I thank you for everyone for joining.
All right. Thank you, everybody, for joining our applied research symposium today. I wish you success in the future, and let the capstone be the Kickstarter that you need. You may feel free to leave the meeting
Thanks.
right now. That should be it. Yep. Thank you, everybody. Have a good night.
Thank you.